Hi everyone, I am Whitroy. Welcome to this audiobook learning video.
Hi everyone, my name is John and I work alongside Whitroy as an electrical tutor.
In this video, we will introduce ASNZS 4836, which covers safe working on or near low voltage and extra low voltage electrical installations and equipment. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 4836-2023. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for the EWRB exam. The official standard is the legal and technical reference. If there is any difference, missing detail, or possible mistake in this audiobook, you must follow the official document. What this audiobook does is take the key ideas from the standard and explain them in simple spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real electrical work. So please think of this audiobook as a learning companion, not a replacement for the actual standard. All right, let's get started.
Section 3. Isolation, fault finding and testing. Today we're moving into Section 3 of ASNZS 4836. This section is about isolation, fault finding and testing. The main idea is simple. Before anyone works on electrical conductors, electrical equipment or exposed parts, the work must be made safe. That means the equipment must be correctly identified, isolated from all energy sources, secured against being switched back on, tested to prove it is de-energized, and controlled so the safe work area is clear. Do not assume something is safe because it looks switched off. Do not assume something is safe because another person said it was off. The safe condition must be proved. Clause 3.1. Isolation. Clause 3.1 introduces isolation. Isolation is one of the most important safety steps in electrical work. In simple terms, isolation means separating the equipment or conductors from every possible source of electrical energy so work can be done safely. But isolation is more than just turning off a switch. The correct equipment must be identified. The correct isolation points must be found. All sources of supply must be considered. The isolation must be secured. Stored energy must be discharged where needed. Then the equipment must be tested to prove it is de-energized. This is the practical process that protects people before work starts. Clause 3.1.1. Isolation principles. Clause 3.1.1 explains the basic isolation principles. Work must not be carried out on or near de-energized, exposed conductors or parts until a competent person has completed the required safety steps. First, the electrical equipment and conductors must be positively identified. The energy sources must also be identified. The isolation points must be identified. After that, the electrical equipment and conductors must be isolated from all energy sources. Then the isolation must be secured, so it cannot be operated by mistake. If stored energy is present, it must be discharged where necessary. For example, capacitors may hold energy even after the supply has been disconnected. After that, the de-energized condition must be proven by testing. The limits of the safe area of work must also be identified. Warning notices must be displayed where needed to reduce the risk of injury or death. The warning message in this clause is very important. All electrical conductors and parts, including neutral and earthing conductors, must be treated as energized until proven de-energized. Always test before touching. This is one of the most important practical rules in the whole standard. If the electrical installation is complex, the isolation procedure should be checked by another competent person. Complex installations may include backup supplies, generator supplies, multiple isolation points, remote control isolators, and safety services. In simple terms, the more complex the installation is, the more careful the isolation process must be. Clause 3.1.2. Identification of electrical equipment and isolation points. Clause 3.1.2 explains that the equipment to be worked on must be positively identified. The points of isolation must also be positively identified. All energy sources must be identified, including non-electrical sources. This means the worker must know exactly what equipment is being worked on, exactly where it is supplied from, and exactly how it can be made safe. Line diagrams, labels, and identification numbers can help with this process. But the important point is this: guessing is not acceptable. If the wrong equipment is identified, the wrong circuit may be isolated, and the worker may still be exposed to live equipment. Clause 3.1.3. Isolation of electrical equipment. Clause 3.1.3 explains how electrical equipment must be isolated. The electrical equipment to be worked on must be isolated from all sources of electrical supply. This may be done by opening switches, removing fuses or links, opening circuit breakers, or removing circuit connections. The worker must also consider alternative power supplies. These may include UPS systems, standby generators, solar supplies, batteries, emergency supplies, ring main systems, neutral backfeed, separate auxiliary control supplies, multiple control supplies, and ELV control circuits that may backfeed through transformers. ELV means extra low voltage. This is an important point because many modern installations have more than one possible source of supply. A switchboard may be supplied by the normal mains supply, but it may also have solar, battery, generator, or UPS connections. A control circuit may appear small, but it may still create a dangerous backfeed. Control circuits or control systems must not be used as the means of isolation. A stop button is not isolation. An emergency stop is not isolation. A selector switch is not isolation. A programmable logic controller, or PLC, is not isolation. The reason is simple. Automatic control devices can operate unexpectedly. Thermostats, switches, PLCs, and interface devices may cause circuit wiring to become energized again. When removing circuit connections, active conductors should be disconnected first. Then neutral conductors should be disconnected. Earth conductors should be disconnected last. Clause 3.1.4. Isolation securing devices and identification. Clause 3.1.4 explains how isolation must be secured and identified. After the isolating device is opened, it must be secured in the open position or in a zero-energy state. The purpose is to prevent accidental operation. No person must operate an isolator or use equipment while an isolation securing device is attached. If the isolation switch has a locking facility, that locking facility must be used. The securing device does not have to be built into the switch, but it must require a deliberate action to attach or remove it. Examples may include a clip, screw, bolt, pin, padlock, personal danger tag, lockout system, permit system, or another system that gives an equivalent level of safety. In simple terms, isolation must not be left unprotected. It must be secured so another person cannot accidentally switch it back on. Clause 3.1.4.1 General. Clause 3.1.4.1 gives the general rule for securing isolation. The isolating device must be secured in the open position or zero energy state. This is done to prevent accidental or unauthorized operation. Where a locking facility exists, it must be used. The safety idea is simple. If someone is working on the equipment, the isolation must stay in place until it is safe to restore supply. Clause 3.1.4.2 Padlocks. Clause 3.1.4.2 explains the use of personal padlocks. Personal padlocks should be used for locking isolating devices. They should be read and uniquely keyed so other people cannot remove them by mistake. Each personal padlock should identify the person who placed it. This includes the person's name, company, and contact details. This may be done by engraving the padlock or by attaching a personal identification tag. If more than one person needs to attach a personal lock to the same isolator, a suitable multi-lock device must be used. The safety idea is very important. Each worker protects their own safety with their own lock. The equipment cannot be re-energized until every person has removed their own lock. Clause 3.1.4.3 Tags. Clause 3.1.4.3 explains the use of tags. Tags must be attached with a lock, string, or tie. The writing on the tag must be clear, readable, and permanent. PVC tape must not be used to secure a tag. If a formal permit system is used, the correct sign-on and tagging procedure must be followed. A tag is a safety communication device. It tells other people that equipment must not be operated, and it helps identify who is involved in the isolation. Clause 3.1.4.3.1 General. Clause 3.1.4.3.1 gives the general requirements for tags. A tag must be attached securely. The information on the tag must stay readable for the duration of the work. A loose, damaged, unclear, or unreadable tag can create confusion, and confusion during isolation can place people in danger. Clause 3.1.4.3.2 Danger tags. Clause 3.1.4.3.2 explains danger tags. Danger tags must be placed at all points of switching, isolation, or disconnection, unless a padlock is used in accordance with the padlock requirements. A danger tag is intended to protect the individual person. In simple terms, a danger tag means someone's safety may depend on that equipment not being operated. It must not be ignored. It must not be removed casually. It must not be treated as just a general warning label. Clause 3.1.4.4 3.3.3 Warning and out-of-service tags. Clause 3.1.4.3.3 explains warning tags and out-of-service tags. A warning tag or out-of-service tag is used when a device or electrical equipment must not be operated, except as shown on the tag. This is different from a personal danger tag. A danger tag protects a person. An out-of-service tag normally identifies equipment that is faulty, incomplete, unsafe, or not ready to be used. Both types of tags are important, but they are not the same. Workers must understand the difference and follow the instruction on the tag. Clause 3.1.4.3.4 Removal of tags. Clause 3.1.4.3.4 explains when tags may be removed. A danger tag may only be removed with the permission of the person who signed it, or according to the approved tag removal procedure. A warning tag or out-of-service tag may only be removed by a competent person who has evidence that the plant or equipment is safe to operate. In simple terms, a tag must not be removed just because the work is urgent or because someone wants to use the equipment. A tag is removed only when it is safe and authorized. Clause 3.1.5 Proving de-energization. Clause 3.1.5 explains how to prove that equipment is de-energized. This is a critical safety step. The voltage tester must first be visually checked for damage. Then the tester must be checked to make sure it is suitable for the voltage that may be present. After that, the tester must be tested on a known live source to confirm it is working correctly. Then the actual circuit is tested. The test must be made between all conductors and a known earth. The test must also be made between all conductors. After testing the circuit, the tester must be tested again on a known live source to confirm that it is still working correctly. This final test is very important. If the tester shows 0 voltage on the circuit, but the tester has failed, the worker may wrongly believe the circuit is safe. So the simple practical rule is this: test the tester, test the circuit, test the tester again. Only competent persons must carry out these tests. This clause also warns about testers that detect the electric field around an energized conductor. These testers are not suitable in all situations. They may not be suitable for screened cables, DC cables, or similar circumstances. DC means direct current. So when proving de-energization, the correct test equipment must be selected for the actual situation. Clause 3.1.6 Temporary bonding of conductors. Clause 3.1.6 explains temporary bonding of conductors. Where the risk assessment identifies the need for temporary bonding, the conductors must be bonded together and connected to the general mass of earth at the work site. The bonding conductors must be suitable to carry the prospective short-circuit current back to the installation earthing system. The conductor should be flexible and not less than 6 square millimeters. Temporary bonding conductors must always be connected together and attached to earth before they are attached to any de-energized part of the electrical installation. Suitable PPE must be used when attaching or removing temporary bonding conductors. PPE means personal protective equipment. The safety idea is that temporary bonding helps control unexpected voltage, induced voltage, or accidental re-energization risk at the worksite. Clause 3.1.7. Identify the safe area of work. Clause 3.1.7 explains that the safe area of work must be identified. All people who will work in the safe area must be told the limits of that area. They must also be told the location of any adjacent, exposed, energized conductors or live conductive parts. The safe area should be identified using barriers or warning signs. In simple terms, workers must know exactly where it is safe to work and where danger still remains. This is especially important where only part of a switchboard, installation, or item of equipment has been isolated. Clause 3.1.8. Work on de-energized electrical equipment. Clause 3.1.8 explains when work on de-energized electrical equipment may proceed. Work must only proceed if the electrical equipment is isolated. Any adjacent exposed conductors or conductive parts in the work area must also be controlled. They must either be de-energized and isolated or separated by barriers or distance based on a risk assessment. The key message is simple. Isolating the item you are working on may not be enough. If there are live parts nearby, those live parts must also be considered and controlled. A worker must not be placed in a position where accidental contact with nearby live parts can occur. Clause 3.2. Fault finding and testing. Clause 3.2 explains fault finding and testing. Before fault finding begins, a visual inspection and assessment of possible component failure must be carried out. The purpose is to decide whether the fault finding can be done with the installation or equipment de-energized. This is important because fault finding and testing on or near exposed energized conductors or live conductive parts can create serious risks. These risks include electric shock, electrocution, arc blast, and flash burn injuries. Before any fault-finding work starts on or near exposed energized parts, a risk assessment must be carried out. The risk assessment must decide whether isolation, barriers, or a safety observer are required. Only competent persons may carry out fault-finding work on or near exposed energized conductors or live conductive parts. When fault-finding near live parts, controls must be used to prevent simultaneous contact with conductors at different voltages, or contact between a conductor and earth. Suitable PPE must be worn or used. The PPE must fit the person correctly and must be in good condition. Fault finding must be done from a stable work position. Before work starts, test equipment must be checked to confirm that it is suitable and operating correctly. The correct test equipment must be used, and the correct operating range must be selected. Special care is needed when working with safety interlocks, control circuits, contactors, terminals, PLCs, and software interlocks. Bypassing, forcing, or bridging these systems can cause equipment to start unexpectedly or become energized unexpectedly. Extreme care is also needed with current transformers. The secondary winding of a current transformer must not be open-circuited because high voltage may be produced. High voltage, or HV, can be generated in that situation and can create serious danger. Care is also needed when inserting fuses or closing links carrying full load current or where a fault is suspected. If work is left unfinished, the workplace must be left in a safe state for other people. Electrical equipment must be returned to service in its original state. If that is not possible, a competent person must assess any changes made to the equipment. After electrical testing of cables, a considerable capacitive charge may remain on the cable. Those cables must be properly discharged to earth before handling. This removes the stored capacitive charge. There is also an important warning about the MEN connection. MEN means multiple earthed neutral. If a neutral earth connection or MEN connection has been removed, it must be reinstated. In New Zealand, the electricity supply industry also uses voluntary rules and guidance from the Electricity Engineers Association of New Zealand. The message is this: fault finding is not casual testing. It must be planned, assessed, controlled, and carried out by competent people using suitable test equipment and safe work methods. Clause 3.3. Testing plug-in electrical equipment. Clause 3.3 explains testing of plug-in electrical equipment. When energized, fault finding or testing is carried out on electrical equipment that plugs into a socket outlet. An isolating transformer or an RCD should be used for protection from electric shock. RCD means residual current device. An isolating transformer must comply with the ASNZS 61558 series. An RCD must be Type 2 30 mA or comply with ASNZS 61008.1 or ASNZS 61009.1. The simple message is that plug-in electrical equipment can still present serious shock risk during energized testing. Extra protection should be used where energized fault finding or testing is required. That brings us to the end of Section 3 of ASNZS 4836. This section gives the practical safety process for isolation, proving de-energization, locking and tagging, temporary bonding, identifying the safe work area, fault finding, and testing. The strongest message is simple. Identify the correct equipment. Isolate it from all energy sources. Secure the isolation. Prove it is de-energized. Control nearby live parts. Use suitable test equipment and PPE. And never assume equipment is safe just because it appears to be switched off.